Joachim is interested in various aspects of astrophysics, and he will be interested in applying for a postdoctoral fellowship at Nordita. And so in that connection, I invited him over to introduce himself to us and gives him also a chance to learn about Nordita. So he will be talking today about the connection between QED and plasma physics. And we heard recently, of course, this talk by Matthias on laser physics. And I believe these topics may be somewhat related to each other. We'll hear more about this in a moment. Please.
Okay, thank you very much for that nice introduction. Like I said, my name is Joachim Lundin. I'm from Lundin University, where I'm a PhD student in Matthias time. So, what I will do now is that I will talk about my research. I will say something about what I have been doing lately and introduce this to you. So the title of the talk is QED and collective effects in vacuum and plasmas. And what I will focus on is, in particular, photon-photon scattering effects. So, I will begin by giving you a brief introduction to what a quantum vacuum is and what photon-photon scattering is. And then I will talk some about how this can be detected and move on to talk about other aspects of the quantum vacuum, dispersive vacuum. I will finish by talking about strongly magnetized system, and this is sort of where we touch base with astrophysics in neutron star environments, vacuum biothermions, and also spin plasmas. The quantum field theory was born out of an attempt to sort of try to merge quantum mechanics and special relativity. And from quantum mechanics, you know, we have the time-energy uncertainty principle, and special relativity have the mass-energy equivalence. And when you merge these two theories, you also merge these two properties. So within quantum field theory, you have the possibility for massive particles to be spontaneously created out of the vacuum, provided they exist over a sufficiently short time driven by this principle. So we have, in the quantum vacuum, we have the pair creation of virtual particles. We call them virtual because they don't exist over asymptotic times. They can only exist for short times. So this leads to a redefinition of what constitutes a vacuum. The vacuum is no longer absence of particles because you always have these fluctuations. Instead, we say that the vacuum is the lowest energy state, which usually implies absence of real particles. In general, the quantum vacuum doesn't give note of itself. You have to disturb it in some way to see the effects of these fluctuations. And the disturbance can be in the form of a electromagnetic field, a strong one, or sometimes, as with the Kashmir effect, we can see effects of the quantum vacuum by simply imposing boundary conditions. Quantum field theory, or quantum electrodynamics in particular, is the theory of matter and photons. We call it QED. You have 8 fundamental interactions in QED, and these are described by these Feynman diagrams. In these diagrams, you can see the time axis in that direction. So something is coming in and something is coming out. So here we have these kind of interactions. They are associated with absorption of a photon, and these interactions are associated with emission of a photon. And then you have different scattering effects, and you have annihilation and pair creation. Alone, none of these processes are real. They do not conserve energy and momentum. But you can combine these kind of diagrams or these kind of processes to form real processes. For instance, if you take photon-photon scattering to the lowest order diagram would look like this. This represents 2 photons coming in and 2 photons coming out. And then you have a some interaction with the virtual fermions inside. Photon scattering. This is a process that has not been experimentally verified yet. I will move on to explain why this is an interesting process in a moment here. This diagram, it shows the cross-section for photon scattering. You see that it peaks somewhere where the photon energy is of the order of the electron resonance. And then the cross-section peaks is about 5 orders of magnitude smaller than the Thomson cross-section. However, in the optical regime, where we have lasers and things like that, the cross-section is very, very much smaller. 10 to the power of minus 40 times that of the Thomson cross-section. But we should not despair.
Sorry, that was for photons. No, what particles was that?
Sorry. You have photon energy here,
Yes.
and this is the cross-section
Yes.
for photon
For
scattering.
what?
Photon scattering.
Photon scattering. But then how come it's related to the Thomson cross-section?
It's not related to the. It's expressed in terms of
Yes.
Thomson cross-section.
Right, just empirical, yeah.
Yeah.
Mm.
Just for comparison. Okay. So, why is this an interesting effect, and why will it be worthwhile to try looking for this? Well, you know that QED is a very well-tested theory, and this is true in particular in this region, where you can have high field, high photon field strengths, high photon energies, but you have low intensity. This is what you can have in particle accelerators, for instance. On the other hand, if you have low photon energy, say optical light, but then instead you use high intensity, then we're moving in this regime. And QED has not been tested in this regime. So this is sort of a new field regime, new parameter regime for QED. So this is one of the reasons why it would be interesting to look for this. And this is starting to become accessible with today high power laser systems. We're not quite there yet, I should say. And if we take the process of photon scattering, because of the small cross section, it can only become experimentally accessible in this regime, I would say.
So to explain this diagram a bit further, can you put some astrophysical sources in this diagram? Where would they lie?
QED and astrophysics.
I mean, in this diagram.
If we
intensity and
take like
frequency.
strong magnetic fields, then you are they have a strong external field, but the effects on, let's say, vacuum birefringence, the effects would act on optical regimes, for instance. So then I would say you're still out here.
Also unexplored.
Maybe.
Untested.
Yeah. I don't know.
Untested QED, you say. Isn't that what you pointed out the corner? It was unexplored QED regime, the lower left?
Out here.
Yes.
Yes. The effect of, let's see. The effect of.
I mean, it's surprising. I would have thought naively low intensity and low frequencies is easy to verify the theory. You're saying that's exactly hard, yeah?
This kind of collective effects where you have you get high field strength is due to the high intensity of that is something which.
So you mean the lower right then, not the lower left? Yes, that was the lower right is the unexplored regime, not the lower left. Yes.
This one, let's
Yes.
next regime.
Yes.
Over here.
That makes more sense. Thanks.
Yes.
Low energy, high intensity. I mean, Isn't this like the photoelectric effect or something, that if you don't have the energy, you don't reach it, no matter how high intensity you have?
That is partly true. You can have, well, you can have, for instance, calibration below the critical Schwinger limit if the field is strongly varying. So you move up in energy instead. So it's sort of, it's not a strict limit. Should we move on?
Please.
So how do we model this? To the lowest order, you can do some calculations, and the contribution from this photon photoscattering will show up as a paramodified Maxwell's equation, where vacuum effects enter as a vacuum polarization and a vacuum magnetization like this. So I don't want to focus on equations too much, but what you can see here is that this vacuum polarization and vacuum magnetization is cubic in the field strength. So the quantum vacuum can act as a medium with nonlinear properties. Because this magnetization and polarization is cubic, this opens for something called four-way mixing. Classically, if you collide two laser beams, nothing would happen. They would not interact. But the vacuum fluctuations, the virtual electron-positron pairs, may mediate an exchange of momentum and energy among the photons. So you can have so you can have scattering. And this allows us for something called three-way coupling. Instead of colliding two laser beams, I can collide three laser beams and get a fourth beam out. This is provided that the incoming beams and outgoing beams satisfy some kind of matching conditions, which corresponds to the conservation of energy and momentum. One such possible system is, I should say, I studied this in the following papers, among other things as well. One such possible configuration is this one. Here I send in two beams of frequency 2 omega and one beam of frequency omega. Then I will get a fourth beam out of frequency 3 omega in a new direction. So we did some calculations for this. We took an example. We used the parameter values from the Astro Gemini laser system that they are just recently operational in the Central Laser Facility at the Rutherford Appleton Laboratory in the UK. Here we have two 100 nanometers, half a petawatt beam beams. And you take one of the beams, you frequency double it, and split it in two, and you get use this configuration. This is a theoretical calculation. This experiment has not been done. The calculation shows that on average you would only get one photon every 10th second. You only have such powerful beams. One photon every 10th shot, I should say. So this is...
In addition to all the other photons that don't vacuum in, there's a huge number of other
yeah,
photons.
this is one scattering event.
Yes.
Every
That's
10
a 3 omega photons, right?
Yeah, so it's harmonics of the laser as well.
So is the difficulty in seeing that simply that you have, so everything is so bright, you can't see the right photons? I mean, how should one technically envisage?
Well, of course you need good shielding, so you only see the part of the interaction region, a small part of the interaction region, which is in vacuum then. And then you can have the direction and color will be unique, of course, polarization, timing. You can also see the signal should be invariant to a small residual increase of the increase of the residual pressure, as well as it should be proportional to the power of each beam. But of course, I think this is a little bit premature for an experiment yet. But if we look a little further ahead, there are prospects of European projects, Eli and Hyper, that will offer a little bit big powerful lasers that will offer exawatt power regimes. And then we're talking about several thousands of scattering events per shot. So this is something that has been investigated if this kind of experiment could be possible to do.
When you say direct studies of the quantum vacuum, what do you mean there? What do you mean?
There are suggested, photon photoscattering is of course one thing that is a direct effect of the quantum vacuum. But there are also ideas of trying to do pair creation directly out of the vacuum with this kind of facility.
Yeah, so that's what you're referring to when you say quantum
Yeah.
vacuum, essentially the annihilation creation process.
Yeah, exactly.
So this cloud thing.
Yes, exactly.
You said in the you're still in the second slide here, but in the previous slide you had the equations, and then you said you wanted to jump over those. Are you going to explain a bit more about the equations later on, or?
A little bit, yes.
So
But in general, I'm
my
trying not to
question
bore
then,
people with equations.
Yeah.
in this
Okay.
class. But we can talk more about
Yeah.
equations. if
Yeah.
you want.
Sorry, with respect to the Astra Gemini system, you said there's 0.1 photons which is scattered
Yeah, on
per
average.
shot. What does it mean per involved photons? So
Pardon?
how many photons are not scattered?
All other photons are not.
Yeah, how many are these? How many are these?
But, pardon?
How many are these?
Oh,
10 to the 15 or
20
so?
something.
Pardon?
10 to the power 20 something.
10 to the power 20.
So I mean, it's enormous.
Okay,
contrast.
yeah. It's clear
I mean,
that it's enormous.
If you could do it ideally, so that everything is vacuum, you have nothing, no other interaction, then I mean, of course, one photon is in the wrong direction is okay, but
Okay.
you will have you don't have ideal systems.
Yeah, okay.
So really strong things. But in this kind of systems, there are experimental difficulties, but it could be possible.
Mhm.
If you go back and look at this diagram, in optical field, the cross-section for photon photoscattering was very small. But if you increase photon energy close to the Compton wavelength or energies close to the electron rest mass, then the cross-section increases dramatically. And QED is very hard to do if you go beyond this limit, beyond for frequency above the Compton frequency, or for field strength above the critical field strength, the QED critical field strength. But still, you can do some things in this region. So here, if you focus on short wavelengths, but you have small amplitudes, so you have it's going to be only a few photons with high wavelengths. And then you can neglect nonlinear effects and focus on effects due to the high frequency. And you get some other corrections to Maxwell's equations that looks like this. You have the Lundin version here, and a small constant. So this will give rise to...
So, sorry, the square is the Helmholtz operator, or what is it?
Yeah, that's the Lundin version. So it's a... Pardon?
Helmholtz operator? Or what is it?
The wave operator.
Pardon?
Wave
Yeah,
operator.
it's Helmholtz operator.
Yes.
Okay.
So.
Yeah.
Remind you of the language, but short wavelength, small amplitude, that basically means high energy, low intensity.
Yeah, exactly.
Yes, okay, thank
That's probably a better way of saying it.
you. Because you had it on the previous slide.
Yeah, true. So this is something I studied in these two papers, and I'll just give you some results briefly. It turns out that within fluids theory, I should say, that these effects can be captured in most cases by just the substitution of the plasma frequency into something which is dispersive. So this is for electrostatic oscillations. They would, because of these QED effects, become dispersive. Also, quantum vacuum modes would be dispersive in this. And if we add a strong magnetic field in the background, we get some additional effects on the equations of motion as well. These effects, strong magnetic fields and frequencies close to the Compton frequency, the quantum vacuum can become quite dispersive. This is dispersion effects can be quite strong. Can I leave this now? This is where it becomes interesting. If we have a strong background magnetic field, I mean, in neutron stars, they are quite, you can have quite substantial magnetic fields, 10 to the power 12 Gauss, usually. And then you get all kinds of exotic physics, like lambda quantization. Atoms become cigar-shaped, and they can form chains of condensates, for instance. I find it interesting that astrophysics, these kind of aspects of astrophysics, is about to move into the are becoming experimentally accessible. You can have, I mean, already today we have detected 200 megagauss magnetic fields in laser solid interactions, where you shoot a high intensity laser pulse on a solid target, and then you get quasi-stationary strong magnetic fields in this region. Quasi-stationary, this means this, somewhat less than a microsecond, but this is several orders of magnitude longer than the laser pulse. And it's believed that that will soon have.
What is this solid in question? Is it a metal or what is it?
Yeah, I think it's usually metal or gold or something. It's believed that soon we'll have gigagauss fields with this kind of schemes. So if we have strong magnetic fields, electron spin effects can sometimes become important. And this is something we investigated in this paper. Electron spins, there is an attractive force due to the interaction of dipole moments. So if the magnetic field is sufficiently strong, it is possible that this attractive force may overcome the repulsion due to pressure, Fermi pressure, and thermal pressure. And this can lead to a genes-like instability. So this is a growth rate in K-space for different wavelengths for the genes instability. And you get sort of a corresponding thing due to the electron spin in a spin plasma. So you can have a similar instability. Of course, you need very high density. But I think it's an interesting effect that I wanted to mention. Yes?
I should leave soon. I mean, you say dipole interaction between electrons was attractive, you said. Does that means you use some sort of wave packet description of the electrons or something? Otherwise, you have to have a charge distribution if you don't have a dipole interaction.
I can show you in more detail how this is done, because it's sort of this is done in an MHD calculation, and there is a way of representing the spin effect in MHD, but I can't do it so briefly.
But I mean, it's not electron-electron, is it? I mean, it's really charge attraction, different charges, which.
Yeah.
But you see dipole, which means you need a charge distribution. You don't get a dipole from a point.
I mean, I think, the instability really probably comes from the Laplacian in the equation for the. If you take the divergence of the electric field, then you have a Laplacian of the. How was it? You have a Laplacian for the charge density, and that's given by something. I mean, you must know this.
Isn't it just another?
I mean,
effect
there's the analogy between the gene sensibility and this instability. I'm just trying to picture what equation I should look at here.
I couldn't.
But here you speak about attracting forces between magnetic moments, yeah?
Yeah.
not between electric charges.
Uh-huh.
Ah,
Maybe
okay.
in common sense.
I thought
Right?
you, I
Is
thought
it-
you meant electric charges, and then you need
I
to
may
charge
have
this
been,
solution
I may have
because you
been
can get it.
not clear on that.
Okay.
Okay. Anyway, moving on. If the magnetic field is very strong, we can also have other effects like quantum electrodynamical effects. And then in particular in magnetars, where the fields can reach or it can exceed 10 to the power of 15 gauss. This is already 2 order of magnitudes larger than the corresponding critical field strength in QED. If this was an electric field, the quantum vacuum would become unstable and we would have pair creation with this kind of field strength. But this doesn't necessarily happen if you have strong magnetic fields. So the magnetic field is allowed to quite substantially surpass the QED critical field strength. And then you can have effects like photon splitting or vacuum birefringence. This is not vacuum, this is birefringent crystal. In a birefringent crystal, the different polarization would experience different refractive index. So things look different depending on which mode we're looking at. So there is an anisotropy within the crystal, and in the vacuum it's the magnetic field that gives this anisotropy. If the field strength is low, then this Feynman diagram will be the most contributing one. And the dynamics is described by Lagrangian, or this is a correction to the classical Lagrangian that looks like this. Now, if the field strength increases, then all these diagrams will contribute. So we can no longer use this expansion term, we need to use a full Lagrangian that looks like this. This is valid both for strong electric fields and strong magnetic fields for arbitrary field strengths. However, if we let the electric field strength be weak compared to the magnetic field strength, we can actually solve this analytically. We need to use some tricks like regularization techniques and Bix rotation. But it can be done. You can obtain a set of QED modified equations in motion for strong magnetic fields. Yes, please.
This Lagrangian, I mean, how has that been deduced? I mean, what is used in order to get that Lagrangian?
You sort of sum over all energy, free energy vacuum states. This was actually done before. This was actually done directly from Dirac's Hall theory
Okay.
before QED. But then it was later derived by Schwinger for forming within QED. It looks the same. So
I have a question.
yes.
The value space that appears in this vacuum effect, they all scale like, they all goes like E dot B and E squared minus B squared. In the previous one, you were showing that F and G and all the terms goes, that depends on essentially square minus B squared and E dot.
Go back to the previous
previous slide.
So back.
slide. Then one forward.
Yes,
Yes.
the F and G
Yes,
goes
yes.
like B squared minus E squared.
Yeah,
And
these are the invariants. They are the same no matter what frame you use.
yes, but the point is that usually if you look at the magnetized magnetar or pulsar, these terms are potentially very small. You can have a very high magnetic field, but usually E dot B is small, and B squared minus E squared is also small.
Why is this one small if you don't have an electric field?
Because you do have electric field.
Okay.
You have some plasma. I mean, you have usually you
Okay,
have force-free conditions, so there is
Okay.
some.
But
in
let's say the
magnetosphere.
surface of the
It is a magnetosphere.
let's say if you say from magnetar, for instance, you only have a decimeter thick atmosphere, and outside the atmosphere you can then you should have.
Well, it's not.
Couldn't you have strong magnetic fields?
It's not obvious. I mean, you have a strong magnetic field, but you can have charges that keeps. I mean, the idea is that E dot B should be almost zero. This is a force-free approximation that you use for the magnetosphere. And also a square minus b square is more or less 0
Mhm.
because
Okay.
that's usually what you solve for the equation. There might be some deviation, but
Mhm.
if you have a gap, what's called a gap, where you have a region where you have a high electric field,
Yeah.
usually you have particle acceleration and percolation, and they shorten up pretty fast in very small
Okay.
distance.
Well, this is very interesting. Okay, I'm learning things now. Anyway, I should move on. So this is how it looks like. We can actually solve this analytically for strong magnetic fields. As I saw previous, it could be interesting to use if I have a plasma, it could be interesting to use a spin to take into account spin effects if the magnetic field is strong. So this can be done with a kinetic approach. If we have use the velocity equation where you include electron spin contribution, dipole forces, for instance. And then the current term in the QED modified equations motion should now be represented by the free current and the magnetization current. So this closes the system. And this is something which I'm looking at in this paper in your physics letters. And I should briefly give you the results. So first, as a first step, we drop the plasma contribution and just look at vacuum birefringence. Here I plot the phase velocity, omega over k, as a function of increasing field strength. And we can see here that this is the orthogonal mode, where the polarization is orthogonal to the background magnetic field. And we have to look at the scales here. But the effects of the vacuum birefringence is very small in this mode. Whereas in the other mode, the parallel mode, where the polarization and the magnetic field is parallel, the effect is very strong and the propagation is strictly forbidden in the asymptotic limit. So already at a field strength of a few hundred, that of the critical field strength, the effect is substantial, and in this case you would have magnetic lensing effects. So surface element of a neutron star will look different depending on what polarization what you're looking at.
So what you're plotting is, you call it b squared, but you really mean omega squared over k squared, yeah? Or what do you mean?
Yeah, okay, yeah, it should be squared.
Yes.
Yeah.
Mm-hmm.
So, I mean, if you look really further out here, then the photons in this mode would be forced to follow the magnetic field lines.
So the critical field strength is what?
The critical field strength is there
Yes,
and there respectively.
Yeah, what is this physically again?
Okay, it's related, it's sort of a translation of the electric field strength, critical field strength, at which you expect a significant pair creation.
Mm-hmm.
And then you translate with this field strength will be if there was a magnetic field. So multiply by C.
Mm-hmm. And the expression, did you have the expression for this on one of the transparencies? Or?
For the critical field strength, no, I don't have it on the
But
transparency.
and for neutrons, would it be when would it be important in the cases you mentioned? You mentioned lasers, you mentioned neutron stars. Do we reach these? In those cases?
Well, I thought we could reach this magnetic field strength in neutron star.
Mm-hmm.
So, of course, if we have electric fields as well, then it's harder to model this because we can't solve the Lagrangian analytically at least, and it's also hard to do numerically.
Yeah, I mean you did this calculation in the red stream, of course, and then therefore there was no E. But you are saying, but maybe you're actually talking about the magnetospheres.
Magnetic field is also smaller.
I mean, I think you're talking about the interior of neutron stars, and you're thinking
Oh,
of,
yeah, I'm talking about the outside.
and you're talking about the
But they're-
outside,
it's the
yeah?
same.
Okay.
Isn't that
There's
what
no-
what-
There's no vacuum in the interior.
Okay, for vacuum birefringence, I mean, this effect is there if there is a plasma, whether there's a plasma or not. But if we look at plasma effects, then of course we're talking about either the atmosphere or
Yeah, right.
interior. Although a plasma description may not be optimal to describe materials.
We can have probably in the very thin atmosphere. So I was thinking the more extended magnetosphere. This
Mhm.
is
Okay. And if we move on, and this is the same system as before, but here just included the spin plasma as well, spin plasma description. So if we look at the parallel mode, the dynamics will be governed by classical plasma effects and QED. You see the classical plasma effects are you don't have propagation below the plasma frequency. This is normalized to the plasma frequency. And also, the slope of this curve, when is the phase velocity. You see the phase velocity goes to, is substantially different from C due to Q, and this is due to quantum electrodynamics effects. You see how it increases with the magnetic field strength. On the other mode instead, the orthogonal mode, we saw from the previous slides of vacuum birefringence that the QED effects in this mode are always small. Also, if you are far from resonance in a strongly magnetized system, that basically means that we're sort of in the optical regime, maybe. For strongly magnetized systems, classical plasma effects can be suppressed, and it's possible to find regimes where the spin contribution to the lowest order is the most dominating contribution.
What is this? Is that again the phase? No, what is it?
This is an effect due. This is an effect due to electron spin. in the
So
spin
when
plasma
you
description.
mean the phase speed, yeah?
Pardon?
By you mean the phase speed?
Yeah,
Ah.
exactly.
And but then there's no K dependence, or is there a K dependence?
No, it's not a K dependence, but it's a dependence on the phase speed will depend on the plasma, on the density, the plasma frequency, and this is an effect due to this.
But I mean, I thought we see from the curve that on your plot there that it's not a constant line. I mean, it's
But this is different
Okay.
modes.
ah,
This is the parallel mode.
yes. I see. Okay. Yes.
So this is the parallel mode is dispersed, and the orthogonal is not dispersed.
Yeah.
Right.
Yes.
Anyway, that's sort of about it. What I had to say.
Mm.
What I've been doing recently. Thank you very much for your attention.
Yeah, thank you very much for your talk. And questions, please.
Questions? Everything's clear to you. You're not expressing to
There are two explanations for no question.
At least.
Can't read my handwriting anymore.
By the way, so in neutron, you mentioned neutron stars. So first of all, this refraction would then be color dependent. Would be different for different colors. So you may, because of this effect, see into different depths, different colors. Is that correct, you think?
Okay. We're talking about vacuum birefringence now.
Right, as applied to the surface of a neutron star, I thought.
not. I mean, things happen if you move up to gamma rays and things like that. Then other effects happen, enter. What we thought, the dispersing effect that we explained, that we looked at in the previous slides. But this back, but in, I mean, if we're looking at optical regimes, then it's probably not strongly dependent on the color.
And for laser application, I mean, forgetting it exactly, was this also supposed to be applicable to laser
Well,
experiments or not?
people are trying to detect vacuum biofluorescence in laser with the lasers, but then you do have cavities, so you have sort of long path lengths, and the magnetic field is on the order of Teslas. It's very hard. I mean, these kind of regimes, it's very exotic for lasers. The laser power is still. Yeah, but the Eli and the Eli sister or hyper systems, and will still be about 3 orders of magnitude below the critical intensity for QED. So,
was this known before that you have this refraction, or?
Partly. This dotted line here is sort of what you get with the weak field expansion. And the asymptotic limit is known, but sort of the intermediate regimes here we haven't had a model for this before.
I see. So that's basically then your prediction that such a thing should occur. Is it fair to say that you are predicting this type of?
Yeah, when I have a theory that describes the whole region.
Yes. So it's the first time that you have a complete theory for which goes beyond the weak field limit. Is that what you're saying?
Yeah, probably. That is probably correct. To at least some extent.
Yeah, I mean, under such conditions, of course, the question whether it applies here or applies there is often a stupid question. Of course, I mean, when Einstein wrote his paper on the E equals mc squared equation, the picture that you got from reading his German paper was that it applies to a torch, and if you turn on the torch and light goes out of the torch, the torch should become lighter. That was the picture I got by reading his paper. There was otherwise no application, of course. So if anybody was thinking, does this guy make any sense, you would think stupid. I mean, of course, even if the torch does become lighter, that is such a minute effect.
What does it matter?
So based on that, one should not judge the theory, of course.
These kind of effects are, I mean,
Because there
there
could
are
be
fundamental
surprises coming up
effects.
later on. What?
There are fundamental effects within QED, so it's interesting from a
Yes,
fundamental point
yes.
of view.
Let me come back to the equations where you had your D'Alembert operator. How did this really come in? Here, for example, yes.
You have, in general, Lagrangian. You sort of do an expansion of this, and there are two things. Generally, you assume that, in weak field theory, I should say, you assume that the field, the external field, is static on length and time scales of the quantum vacuum fluctuations. So this means that the frequencies are much lower than the Compton frequency, and also the field should be much smaller than the critical field strength, so you don't have pair creation. So these are the two approximations. If you increase the field strength, so when you get this term, then you assume that you're far from the Compton, that the frequency is much more than the Compton frequency, and then you expand the Lagrangian around the field strengths. So this is a smallest contribution due to the field strength. But whereas in this case, then you expand it because of high photon frequencies instead. So this is the same Lagrangian but different expansions. So you take account into different effects due to.
Yeah, you see. So it really is a more complicated version of magnetization effects and deviations from vacuum permeability in a
Yeah.
non-trivial way. So that's it's not a vacuum in that case anymore then. That's exactly when it's not a vacuum.
Magnetized.
Well, that's what you're saying. So it is a vacuum as far as material is concerned, but it's
it's the vacuum.
but there's a magnetic field.
This one, okay,
the strong
this doesn't require external.
It's a polarizable medium. The vacuum.
So it's not a vacuum.
It's not in the usual sense of vacuum because
No.
you can polarize it and you can magnetize
Yeah,
it.
okay, yeah.
Yeah.
That's true.
Not in the classical sense.
The vacuum acquires properties of the dispersant.
I see. So it really actually means the actual Maxwell equations really break down.
Yeah.
Yes. Interesting. Very good. That's opposite to what we normally teach in astrophysics, of course. But that's good to know that there are these limits, of course. Any other questions? Yes, please.
So, in when you reach the, let's say, 500 keV or something like that, and you find this dispersive effect due to the vacuum polarization and other things. So, do they give you any polarization angle rotation, like Faraday rotation for regular dispersive? I mean, because there are ideas of building polarimeter in that kind of 100 keV regime.
Yeah.
So it would be nice. I mean, if there is a possibility of having some polarization radiation moving through this vacuum and getting rotated in angle, you might be able to detect the rotation. That would be a constant number. And it's not in optical, so you are much closer to the regime where you would expect your effect to be important.
So yes, I can't answer exactly how that's
What was the question again?
No, I mean, if you have dispersive effect,
Yes.
you have rotation of the polarization plane like Faraday.
Yes, right.
And
Exactly.
so it's polarization usually measured in optical,
Yes.
but there are ideas of measuring it in X-ray with the next
Yes.
generation instrument.
Right.
And that will be in the 100 keV regime much closer to the energy where you would expect this effect to be dominant, and the
Mhm.
cross section for all this process to be much higher. So I don't know this photon inversion. I don't know if that could be something worth looking at. We'll try to make an estimate. It might be a very small number, but I don't know. That could be something.
Yeah, I mean, basically, the question is, I mean, if you're not doing QED, you would be doing light with polarization, of course. And that means you're doing radiation transfer with Stokes parameters and stuff. So it's asking how the polarization plane, of course, tilts and whether magnetic effects
Yes.
on this tilt.
So,
But that is, yes. That's not embodied by those equations in any obvious sense, or is it?
no, I mean, I just saw that there's dispersive properties of the medium. So
Well, it should be
there should be some
included in the first version with the nonlinear terms, no?
In
Shouldn't
the
it?
first version?
Well, the general version where the nonlinear
Yeah, exactly.
magnetization and
Probably so,
polarization were included. And
You mean
these
when you had
equations
the-
should cover this effect, shouldn't they?
This one? Uh-huh.
Because it's simply a polarizable and magnetizable medium, which usually creates some sort of rotation.
yes.
And this is a medium in some sense, and the same, with the same behavior, qualitatively. So it should be embodied there, shouldn't it? I would guess.
Not an expert on that. I just gave an
Isn't
idea.
this medium, that's sort of this instantaneous creation annihilation things in fields, isn't it?
But
Is that the
here,
vacuuming question?
here it is modeled like a usual medium in this form, but a nonlinear one. This is the only exception in some sense, or the only new aspect. In all other respects, it looks like a usual medium.
Yeah, that I know.
Mm-hmm.
Yeah, right. Therefore, I was talking in terms of using the language of magnetization and this. What is it called? This is epsilon.
Polarization.
No, epsilon is the permeability. Yeah? No.
Dielectric constant.
Dielectric constant. Yes. But that's something else. It's truly a breakdown of Flach of the Maxwell equations, of course, which just have similar appearances. Yes, I see. So there will be more time, of course, for discussions. You have time this afternoon still, and we'll have more discussions in an informal way here after lunch. Okay, thanks again.